Now questions from a miscellaneous exercise. If A is a matrix of order 3, and look, all elements are 1, then prove that A raised to n is matrix of order 3 having all entries 3 raised to n minus 1. We prove this by principle of mathematical induction. So let me take this as a statement En, statement for natural numbers. P of n, A raised to n, 3 raised to n minus 1, 3 raised to n minus 1, we say this is statement En. Now for n equal to 1, here left hand side is A raised to 1, that is A, and right hand side is, putting here n equal to 1, RHS is 3 raised to, everywhere taking 1, 1 minus 1 is 0, 3 raised to 0, 3 raised to 0, all entries are 3 raised to 0, so it is 1, 1, 1, 1, 1, 1, and it is A. So LHS is equal to RHS. Therefore, LHS is equal to RHS. So statement is true for n equal to 1. So P of 1 is true. Now second part. Suppose that P of A is true. Statement is true for n equal to A. So that means putting n equal to K, LHS equal to RHS. So E raised to K is equal to 3 raised to K minus 1, 3 raised to K minus 1, n is replaced by K, here K. So this is true. We suppose that statement is true for n equal to K. Now using this, we are showing proof for n equal to K plus 1. So proof for n equal to K plus 1. LHS is equal to A raised to K plus 1. So it is A raised to K into A. Now substituting values, this is A raised to K. So A raised to K is 3 raised to K minus 1, 3 raised to K minus 1, it is A raised to K into A. Matrix A is given, it is 1, 1, 1. Now multiplying these two matrices, as we do multiplication, multiplying first row with these columns, say up here, By this procedure of multiplication, 3 raised to k plus 1 into 1, 3 raised to k1 minus 1 plus 3 raised to k minus 1 into 1, 3 raised to k minus 1 plus 3 raised to k minus 1. So product of these two numbers plus product of these two numbers plus product of these two numbers. Now multiplying with second column. Again pattern is same. So this will be repeated. 3 raised to k minus 1, 3 raised to k minus 1, 3 raised to k minus 1. Again 3 raised to k minus 1, 3 raised to k minus 1, 3 raised to k minus 1. So turn of first line is over. Now turn of second line. Again, because elements are same, so this will be repeated. So 3 raised to k minus 1, 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 k minus 1. So it is equal to, this is 3 times 3 times 3 raised to k minus 1, 3 times 3 raised to k minus 1. This is 3 times 3 raised to k minus 1, 3 times 3 raised to k minus 1. Every element is same. 3 times 3 raised to k minus 1, 3 times 3 raised to k minus 1, 3 times 3 raised to k minus 1, 3 times 3 raised to k minus 1. So this is 3 raised to, say this is 3 raised to 1 into 3 raised to k minus 1. So adding these indices, because bases are same, so it will be 3 raised to k plus 1 minus 1, 3 raised to k plus 1 minus 1, 3 raised to k plus 1 minus 1, 3 raised to k plus 1 minus 1. So all entries are same, and you can see that here n is replaced by k plus 1. Everywhere n is replaced by k plus 1, so that is right hand side for n equal to k plus 1. So it is RHS. This is RHS for n equal to k plus 1. Therefore, statement is true for k plus 1. Thus, P of 1 is true. P of 1 is true. Second, supposing that P of k is true, statement is true for k plus 1, k belonging to n. Therefore, this is true for every n belonging to n. So, this question is proved using principle of mathematical induction. One more similar question. Here E is given. This is A. And prove that A raised to n is 1 plus 2n minus 4n and 1 minus 2n. So let me say statement for natural number n is any positive integer. Say Pn is, this statement is a raised to n is equal to 1 plus 2n minus 4n and 1 minus 2n. This is a raised to n. Statement for n natural number. Now we prove this by principle of mathematical induction. So for n equal to 1, left hand side is a raised to 1. It is a. Right hand side is putting here n equal to 1. Say giving here 1. So 1 plus 2. 1 plus 2 into 1 minus 4 into 1. Here 1. 1 minus 2 into 1. So this is 1 plus 2, 3. It is 3 minus 4, 1 minus 1. And say it is a. This is a. So LHS is equal to RHS. Therefore, LHS is equal to RHS. So P of 1 is true. Now second, suppose that statement is true for n equal to k. Suppose that P of k is true. So we accept this without proof for n equal to k. So e raised to k is equal to 1 plus 2k minus 4k k 1 minus 2k true for n equal to k. So we accept without proof this is true. Now using this we prove that statement is true for n equal to k plus 1. For n equal to k plus 1. Now showing proof. For n equal to k plus 1, left hand side is a raised to k plus 1. Now a raised to k plus 1, it is a raised to k into a. Now using value, this is a raised to k. Using this value of a raised to k is 1 plus 2k minus 4k k 1 minus 2k into a. A is 3 minus 4 1 minus 1. Now multiplying this matrices. See first row multiplying with first column. 1 plus 2k into 3, that is 3 plus 6k plus product of these two numbers. So this is multiplying with first column. Now with second column. Multiplying this with minus 4 minus 8k plus product of these two numbers, that is plus 4k. Now turn of same line. K into 3 is 3k plus product of these two numbers plus 1 minus 2k. Now multiplying this with second column, k into minus 4 is minus 4k. Product of these two numbers minus 1 plus 2k. That is 3 plus 2k minus 4k. Here 3k minus 2k is k plus 1. This is minus 2k minus 1. Now look, we want right hand side for n equal to k plus 1. Now see, we convert in this pattern. We want right hand side for n equal to k plus 1. So we want here k plus 1. K plus 1. See, arranging accordingly, here, say look, 3 can be expressed as 1 plus 2. 1 plus 2 plus 2k. Then here, minus 4 k passages. This is k plus 1. Here, minus 1 minus 2k. Somewhere here done mistake. See here, this can be expressed as 1 minus 2 minus 2k. Minus 1 is expressed as 1 minus 2 minus 2k as it is. Because we want this pattern. Here we want k plus 1. So that is equal to 1 plus, from this part 2 common, inside k plus 1. Here minus 4 common, k plus 1. This is k plus 1. And here 1 minus 2 common, k plus 1. And you can see that we have obtained this pattern. N is replaced by k plus 1. So this is the RHS for n equal to k plus 1. Therefore, statement is true for k plus 1. Thus, P of 1 is true. Second, P of k is true implies statement is true for k plus 1. Thus, this is true for every n belonging to n. If A and B are symmetric matrices, prove that this is a skew symmetric matrix. Say here A and B, these are symmetric matrices. And by definition of symmetric matrices, because A is symmetric matrix, so transpose of A is equal to A, and transpose of B is equal to B. So this will be used in calculation. Now we want to show that AB minus BA is a skew symmetric matrix. We want to show that AB minus BA is a skew symmetric matrix. Now, what is the definition of skew symmetric matrix? If transpose is equal to its additive inverse, means if X is a skew symmetric matrix, if X is a skew symmetric matrix, then its transpose equal to its additive inverse. This is conversely also true. Any matrix is a skew symmetric matrix, X dash is minus X. We have definition. X dash is minus X, then X is a skew symmetric matrix. So here we want to show that this is a skew symmetric matrix. So what we shall do? We shall prove that. We will prove that EB minus EA, its transpose equal to, its transpose is equal to minus of that matrix x dash equal to minus x. So x is a skew symmetric matrix. Application of this definition. Now here EB minus EA whole dash, this can be expressed as EB dash minus BA dash, because we have property x minus y whole dash or transpose of x minus y is equal to transpose of x minus transpose of y. Then using here property, transpose of A into B is equal to B transpose into A transpose minus transpose of BA, that is equal to A transpose into B transpose using property. Now B transpose is B, B transpose is B, A transpose is A. So BA minus A transpose is A, B transpose is B. So now taking minus common, AB minus BA. So result is true. So this is a skew symmetric matrix. Now here, show that matrix B dash AB is a symmetric or a skew symmetric according as A is symmetric or skew symmetric. We take case 1. Suppose A is symmetric matrix. A is symmetric matrix. If A is symmetric matrix, then transpose of A is A. A is symmetric, transpose of A is A. Now question is, if A is symmetric, this will be symmetric. So now we are going to show that B dash A B, this is symmetric matrix. If A is symmetric, show that this is a symmetric. Now to show that it is a symmetric, we show that its transpose is equal to itself. So its transpose is equal to matrix itself. If x dash is equal to x, then x is a symmetric matrix. Now here we use property. This can be expressed as B dash into, keep association of A and B in bracket. B dash into EB, keeping A and B bracket. Now next step, using here property of transpose. Say we know that x into y, its transpose is equal to y transpose into x transpose. So here we use that property. Suppose this is x, this is x, this is y. X into y transpose is equal to y transpose into X transpose. This is used. X into Y. Transpose of X into Y is Y transpose into X transpose. Now this is AB transpose. That is again here using property B dash into A dash. Complement of transpose of AB is B transpose into A transpose into transpose of transpose is B itself. Now look, A dash is equal to A because from 1 A dash is A. This is from 1. So result is true. Now case 2. Case 2. If A is a skew symmetric matrix, A is skew symmetric matrix. If A is skew symmetric matrix, then its transpose is equal to its additive inverse. We will use this result. And so we want to show that this will be also skew symmetric. Now, to show that it is a skew symmetric matrix, we have to show that its transpose is equal to its additive inverse. If x dash is equal to minus x, then we can say x is a skew symmetric matrix using this rule. X dash is minus x, then it is a skew symmetric matrix. So x dash is minus x. If we can prove this, we can say x is a skew symmetric matrix. And in this proof, we will use this result as well as this property. So say here, again, I am keeping association of AB. So B dash into AB, it's a complement, it's transpose of B dash into AB. Now again, using this rule, similarly as in case 1, if this is x, this is y, x into y, transpose of x into y is transpose of y into transpose of x. Again, transpose of AB is B transpose into A transpose, and transpose of transpose is B itself. Now here A dash is minus A, so replacing A dash by minus A. So B dash into minus A into B, because A dash is minus A. So this is from 2. Now this is scalar, minus 1 scalar, putting outside. So minus of B dash into A into B. So we have proved that x dash is minus x. So x dash is minus x. So this is skew symmetric matrix. For what values of x, this product is O. This is zero matrix. Say here, first of all, we multiply this row matrix into this square matrix. Say doing multiplication, multiplying first row with first column. 1 into 1 is 1, plus 2 into 2 is 4, plus 1. Then go on next. 1 into 2 is 2, 2 into 0 is 0, 1 into 0 is 0. Then go on next. 1 into 0 is 0. 2 into 1 is 2. 1 into 2 is 2. Multiplication is over. Then this is 0 to x equal to 4. So it is 6 to 4. This is column matrix. 0 to x equal to 4. So this is 1 by 3. This is 3 by 1. 1 by 3. 3 by 1. So product will be 1 by 1. Matrix containing only one element, that will be product on left hand side. So this row multiplying with column, 6 into 0 is 0, plus 2 into 2 is 4, plus 4 into x is 4x. So this is only one element, 1 by 1 matrix. It is 1 by 1 matrix. It is 4x plus 4. This is 1 by 1 matrix. And because it is 1 by 1 matrix, keep here 0 matrix containing only one 0. So this is equal to a 0 matrix containing only one 0. So comparing both sides, 4x plus 4 is 0. So x is equal to minus 1. Find the matrix x so that this equation is true. Say here, this matrix, its order is 2 by 3, 2 rows, 3 columns. And because x is multiplied with this matrix, this multiplication is defined if number of columns in x is equal to number of rows in second matrix. So here in x, number of columns should be 2. Number of row, suppose m. Now see, this matrix is matrix 2 rows, 3 columns. Now look, multiplying x with this matrix, this is the result, 2 by 3. This product is defined if these two are equal. And as we discussed, when these matrices, two matrices of this order are multiplied, its product will have order m by 3. So this is m by 3. So what is m? M is 2. So this value should be 2. So here, if x is a matrix of order m by 2, that is 2 by 2, of order 2 by 2, then on left hand side, then equation exists. And we want to find matrix x. So suppose that x is, because x is 2 by 2 matrix, x is A, B, C, D. So putting in equation, so equation will be, putting here value of x, A, B, C, D into 1, 2, 3, 4, 5, 6 equal to minus 7, minus 8, minus 9, 2, 4, 6. Now we solve this equation. So multiplying AB with these columns, see A into 1 is A plus into 4 is 4b. A plus 4b. Then multiplying with this column, this is done. Now with this column, 2a plus 5b. Then with this column, 3a plus 6b. 3a plus 6b. Now turn off second line. Now A and B will be replaced by C and D. So C plus 4D, C plus 4D, 2C plus 5D, 3C plus 6D. It is equal to minus 7, minus 8, minus 9, 2, 4, 6. Now comparing both matrices, A plus 4B is equal to minus 7. 2A plus 5B equal to minus 8. 3A plus 6B equal to minus 9. This is set of three equations. Then fourth equation, C plus 4D is 2, 2C plus 5D is 4, 3C plus 6D is 6. So these are equation 4, 5 and 6. Now we solve these two equations. Solving equation 1 and 2. Still, this equation I multiply by 2. 2a plus 4b is minus 7. 2a plus 8b multiply by 2. 2a plus 8b is minus 14. This is multiplied by 2. Second equation will be as it is. Taking subtraction, minus minus plus. This will be cancelled. 8 minus 5 is 3b is 8 minus 14 is minus 6. So b is minus 2. Therefore, b is minus 2. Putting value of b in equation, put in 1, a plus 4 into minus 2 is equal to minus 7. b is minus 2. So a is equal to minus 8 taking on this side, so 8 minus 7. So a is 1. So a equal to 1 and b equal to minus 2. So solution of 1 and 2 is a1, b minus 2. Now putting here a1 and b minus 2. 3 into 1 is 3, minus 12, minus 9 is 2. So equation 3 is also true. For which equation 3 is also satisfied. Now to find C and D, we solve equation 4 and 5. Now solving equation 4 and 5, this is 4. I am multiplying by 2. So 2c plus 8d is equal to 4. 2c plus 8d is 4. 2c plus 5d equal to 4, I think as it is. Now taking subtraction, 3d is 0. So D is 0. Therefore, D is 0. Putting this value of D in equation number 4, putting here D 0, C is 2. Therefore, C is 2 and D 0, that is solution from these two equations. Now check equation number 6. In 6, if you keep here 2 and D 0, so say 3 into 2, 6. 6 is equal to 6. So this is true. So for which equation 6 is also satisfied. All corners should be equal, L is equal to R. This corner to corner should be equal to 2. Thus, matrix X is putting values of A, B, C, D. A we have obtained 1, B we have obtained, B was -2, C is 2, D is